Step right inside the memory palace with me. Imagine you're standing in this vast, echoing corridor, and right ahead of you are several locked doors. Now, behind these doors, that's the complete mastery of the Cambridge IGCSE Computer Science 0478 syllabus. The whole shebang. But right now, you're stuck in the hallway, and honestly, your exam grade boundary is at serious risk. Why? Because you might actually be carrying a massive, fundamental misconception straight into the exam room with you. It's something examiners see over and over and over again. So, let's unlock these doors one by one and lock in those top band marks.
Listen to this statement for a second. Computers have microscopic ones and zeros inside their memory chips. Okay, if you write this, or honestly, even if you just kind of think this while you're framing your exam answers, you are falling into an incredibly painful mark-losing trap. I mean, it sounds logical, right? But it's a critical mistake. It screams to the examiner that you lack foundational understanding. Examiners are hunting for absolute precision, and this kind of answer, it'll instantly cap your score. So let's fix this right now and get that first door unlocked. Okay, let's dive into this. Room 1, the foundational room. To progress any further in our memory palace and, actually secure those high marks, we have got to unlock the absolute truth about how computers really handle information. We've got to strip away the myths and get right down to the bare metal of computer science. Here is your official Cambridge Safe definition. The binary number system is a base 2 system using only 2 values, 0 and 1. Think about it. A computer is just an electronic machine for processing data, right? But it absolutely cannot inherently understand numbers, words, images, sounds, or video the way that you and I do. All of those complex types of data, they must first be turned into this base 2 format so the computer can actually do something with them. No matter how insanely complex the system is, the basic building block in literally all computers is this binary system. All right, so if there are no physical microscopic numbers floating around inside the microchips, what does this 0 actually mean? Well, this number is really just a convenient, human-readable way of representing an electrical signal in an off or negative state. Literally, if you were to crack open a computer and look deep inside the processor, you wouldn't see a little 0 sitting there. You would just see the absence of an electrical charge at a very specific point in a circuit. It's a pure electrical reality that we've just translated into a mathematical symbol to make our lives easier. Now, contrast that directly with the number 1. In the binary system, the 1 simply represents an on or positive electrical state. And it's exactly this simple duality, on and off, 1 and 0, that forms the absolute bedrock of all computer processing. Every single piece of information your computer has ever processed is just billions of these microscopic switches turning on and off in incredibly complex patterns. Mind-blowing, right?
Moving deeper now into room 2, the translation room.
And this brilliantly illustrates how things scale up. Knowing about on and off switches is great, but we really need to see how these tiny individual states scale up into larger, meaningful data that you're actually going to be tested on. When we string these binary bits together, we give them column values, exactly like we do in normal math. In an 8-bit system, we use base 2 powers. So starting all the way from the right, we have 2 to the power of 0, which is 1, then it doubles, 2, 4, 8, 16, 32, 64, and finally 128 on the far left. A typical 8-bit binary number uses these very specific column headings to build a value. If there is a 1 under the 64 column and a 1 under the 4 column, you literally just add them together. It's just beautifully systematic. To really make sense of it, just compare binary to the base 10 denary system that we use every single day. Our daily math uses column headings of 1, 10, 100, 1,000, which if you think about it are just base 10 powers. We use 10 digits, 0 through 9. Computers use 2. Simple as that. Oh, and by the way, while binary is what the computer hardware physically uses, you'll also absolutely need to know about hexadecimal. That's a base 16 system, and it's another highly efficient system used by programmers to represent this binary data in a much more compact, human-readable way. Okay, we are making really great progress here, but pause for just a second. What is the hidden clue for top marks? In a few moments, I'm going to reveal the exact hidden examiner clue, literally a specific phrase that upgrades a failing generic answer into an elite top band score. Seriously, it's a real game changer. But if you tune out of this explainer right now, you'll miss it entirely, and frankly, you need to unlock the framework in the next room first, otherwise that clue won't even make any sense to you. So let's keep going. Room 3, the logic room. Now, what's really interesting about this next concept is that we transition from just storing data to actually making decisions with it. This room is governed by Boolean algebra. That is the complete absolute basis of computer arithmetic and modern circuitry. Notice how normal everyday language maps so directly onto binary notation. In computer science, Boolean expressions can produce values when they're evaluated, and there are only ever two Boolean values, true and false. True seamlessly translates to 1, on, yes, or positive, while false translates directly to 0, off, no, or negative. And Boolean expressions can compare data of any type, provided both parts of the expression have the exact same data type. It bridges that gap between human logic and electronic processing perfectly. So, to actually process this Boolean logic, computers use what we call logic gates. When you combine several logic gates together, you form a circuit. Now, these gates receive binary data as an input. They apply a specific Boolean operation using these logical operators, which are and, or not, and then they spit out a binary result. It is a highly predictable, entirely rule-based system that allows for all the design and crazy performance we see in all modern computers today.
All right, the stakes are getting higher. Welcome to room 4, the examiner's room. The stakes are absolutely at their highest right now because this is where theory meets reality. You could know literally everything about binary and logic gates, but if you don't know exactly how the examiner expects you to write it down, you are going to drop marks, period. So we are bringing out the high mark strategy framework specifically required for the Cambridge 0478 exam. First up, you have to decode the command words. If a question says state or define, the examiner wants concise precision. Absolutely no waffling allowed. Describe means you need to list out the technical characteristics. Explain demands the why and the how. Calculate means you absolutely 100% must show your working. And evaluate requires context and your judgment. Listen, examiners are looking for distinct technical points based on these specific words. If you write generic answers or if you use the wrong nouns for the scenario they gave you, you will lose marks for sure.
So, the crucial point is this elite 4-step framework. This right here is exactly how you transform a weak answer into a top-band response. Step 1, identify the concept. Step 2, extract the evidence or the data straight from the scenario. Step 3, apply scientific reasoning to connect them. And step 4, polish it off with exact examiner wording. Keep in mind, 1 mark normally needs 1 completely distinct technical point. Please don't just repeat the exact same idea in slightly different words. It doesn't work. Let's actually see this in action. Take a look at this classic spot the error moment. This catches out thousands of students every year. Validation versus verification. Yeah, they sound incredibly similar, but confusing them is a fatal error. Validation is purely a reasonableness check, like is the data sensible and does it fall within acceptable boundaries? Verification, on the completely other hand, is simply checking that data was copied or entered correctly without any accidental changes. Using precise terminology like this, it's not optional, it is mandatory for unlocking those final marks. Let's finally close that open loop from earlier. Let's look at a flawed student answer explaining why a computer uses binary. Ready? Because computers have ones and zeros inside them. Boom, 0 marks. let's finally close that open loop from earlier. Let's look at a flawed student answer explaining why a computer uses binary. Ready? Because computers have ones and zeros inside them. Boom, 0 marks. Now compare that to an upgraded top-band answer using our new framework and that exact examiner clue. Here we go. Computers use the binary system because they are made of electronic circuits and memory that rely on tiny switches. These switches only have 2 electrical states, an on state represented by 1 and an off state represented by 0. Did you catch it? That exact phrase, 2 electrical states, is the hidden examiner clue. That right there is what upgrades a failing generic attempt into a perfect top-band score.
Now, to ensure you never fall for these exam traps again and always have the exact frameworks you need at your fingertips, there is one crucial step you should take right now. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Staying plugged into this channel is literally a fantastic way to protect your grade boundary and build your absolute confidence going into that exam room. We've conquered the foundational rooms, but honestly, an immense challenge still remains. How do you actually apply this 4-step framework to the highest stakes, most intensely difficult evaluation questions on the paper? Well, the final room in our memory palace remains securely locked for now. The ultimate top-band evaluation framework is actually trapped inside our next explainer. So, what's it going to be? Are you prepared to risk your grade by stopping right here, or will you take the next step and unlock that final door? Jump into the next explainer right now, and let's finish what we started.